We got a black disc. Which falls subject to gravity. But which adheres to the wall. In either facial orientation. Hold on, let me go rescue that from the heater here. Yeah. Including edge on. So apparently, no matter what I do, it's attracted to the wall. No, apparently, whatever I do, it's attracted to my whiteboard, which is interesting. Got another one. Which is not attracted to the first one. In fact, which pushes the first one away. In this particular orientation, so as long as I was testing orientations, I started, okay, what about that? Okay, so now not only, now they are attracted to each other? Okay. Does that work? I'm just thinking about variables now. Does that work if it's not on the whiteboard? Whoa. So I'm going to let go of the one on top. And it's projected up and away. Unless, whoa, unless I change the orientation. So again, we've got this, whoa, this, the repulsive orientation, I guess. Oh, wait, I guess it flipped upside down. So we've got one orientation where there's an attraction. And another orientation where come back here, where there's, oh, well, that's odd. All right. I was sort of hoping that I could get it to balance there. But it's trying to trying to flip. I don't know if that's coming across. I'm just relying on that repulsion, and it's twisting around. And finding the other orientation. Huh. Okay. All right. So enough with the phone. Yeah. Which? Like this is magic. I think it is going to flip every time because it's trying to find a lower energy state. What are these things? I don't know, but I found them. I found them in a pile of rocks in a region to the east of Greece that is now in Turkey called Manisa, which is which is a sort of an updated name of what it used to be called Magnesia, Magnesia. So what am I going to call them? I'm going to call them magnesia rocks. No, you don't like that? All right, we'll do it that way. Obviously, these are magnets. And perhaps obviously that's what we're talking about in chapter 27. Permanent magnets, magnesia rocks, in other words, mag rocks, I like it, are attractive. They attract unmagnetized metal objects like the metal backing of the whiteboard, which is there, although we don't know it, and which helps explain why the mag rocks are not attracted to the drywall in the same way. A compass operates on this principle. A permanent magnet does appear to be orientable. It does appear to evidence different behavior if we reverse the orientation. We saw that when we looked at those disk magnets. If we oriented them one way, they attracted. If we oriented the other way, they repelled. Just like so that's almost identical to the behavior that we observed, the phenomenological behavior we observed when we were talking about abrading a plastic rod with fur and then abrading a glass rod with silk that we got two different flavors of thing to happen. Two charged plastic rods repelled each other, two glass charged rods repelled each other, but the plastic and the glass attracted to each other. So he's okay, there's got to be, it's not just that it's charged a particular way, and it appears to be a binary. That was way back in the very first unit we talked about electric charge, and why have we made it up the way that we did. And it was just to put a model to a binary behavior that we observed. We're going to do exactly the same thing with this. Call them red and blue. Call them positive and negative. No, positive and negative are taken because we talked about charge. Okay. Call them, hey, if I put a rectangle of that material, if I place it in some water, float it in water, it will rotate as I rotate. And one end of it will always point towards the direction which I have agreed with my friends over here is north. Okay, so one side of this rectangle always points north. Okay, I'll call it the North Pole. I'll call one of the sides of this thing north, and I'll call the other side south. Why? Because it has something to do with the direction that I called north in the first place. If we had called the direction towards Polaris some other thing, if we had called it, I don't know, squirrel, then we'd be talking about a squirrel magnetic pole. Like that, it's just the way, there's nothing fundamental about north or south, or has nothing to do with anything except that the compass points north. Opposite poles attract, like poles repel. Sounds familiar? That's what happened with charge. So we're going to call them north and south. And we can tell the difference because we are able to orient them for geographic north. Fine, you put them both in water and allow them to reach their orientation. So okay, both of those are north poles. So if I point them towards each other, they repel. And if I flip them around and point them towards each other, now they attract. Okay, so now we've got, you know, a mechanism. This feels a little bit slow, I imagine, to underscore the fact that so much of what we know now about magnets and take for granted is derived knowledge. It started in like 600 or 800 BC when what I just did with those two magnesia rocks is what they did. They say, hey, good, click. Whoa. And then it was phenomenological. It was a completely observational, completely qualitative, these behave differently. And for a while, they were regarded as like magic, or like there was a huge superstition about them that they were like possessed, or whatever the like prevailing sort of cursed, or I don't know, that there was some magic to that. After they became used as compasses, a lot of that superstition sort of went away because it was more commonplace. It was more like, oh, that's just the thing. That's the thing that does the thing. Okay. But that's all we had for like 1,000 years, close to 2,000 years. Certain metals, like a metal nail, respond to the presence of one of these permanent magnets, these magnesia rocks. So this is a slide that only says what we already knew experimentally, sort of phenomenologically. We can see that there is an attractive force. Those magnets stick to the wall. And if we had a piece of metal that we could experiment with, we would see that that attraction was mutual, that they would attract towards each other. We've drawn it with a force vector, but we actually have no way of measuring that force. I mean, I guess we could attach it to some kind of force meter and figure out how strong that force is, but we have no other way to be quantitative about this so far. This action at a distance, when I was using one magnet to push the other one around the whiteboard, they didn't touch, which is a little bit non-Newtonian. In order to apply a force to something, we've got to contact it, right? And this is not that, which makes me think again about one charged object repelling another charged object without actually touching it. That this is action at a distance the same way as we've seen already, which means what I'd like to define is a field, some sort of field that keeps track of the interaction between these magnesia rocks. For now, I don't have any other way to quantify that field except to say that a compass needle responds differently if I put it in different orientations near a permanent magnet. Okay, so we take a permanent magnet and we have them north and south, and we'll shade the blue side, that will shade the north side blue. And the same thing for the compass needle. The compass needle points north, where it's blue. So because north repels north, if we put the compass here, north points away. Okay, and if we take a sort of neutral compass and put it at that spot, it will sort of snap to really quickly and only oscillate very small, like very small oscillations from that direction. If we put the compass here instead, neutral compass, stick it at that spot, it will align, but it won't be quite so vigorous in its alignment. It will align, it will point that way, but it'll be sort of loose. And if we jiggle the compass, that needle will sort of slosh around there. It's not a very strong alignment, whatever that means. And if this feels goofy and made up, it should, because it was. This is how science worked for a while. All right, so we can talk about a magnetic field, I suppose, some sort of effect on the space around the bar magnet that changes how permanent magnets respond to it. Little compass needles respond in the presence of this permanent magnet according to the magnetic field. It appears to be stronger the closer we are to one of the poles. If we put the compass here equally far away from the South Pole, we get an equally strong snap to alignment. It just points towards the south instead of away from the north. So, all right, the strength of the alignment, call that the strength of the field. Why not? call it B because that seems perfectly confusing. We certainly wouldn't want to call it M for magnet. And in fact, it turns out there's a really good reason for making that distinction. Magnetization is the thing that we'll use vector M for, and the field as sort of expressed outside a bar magnet, we can use some other symbol, and B is where we landed, I guess. Because we're farther away, this vector is weaker, and it's not as long, and it points in the direction of the compass arrow. This one is a little bit stronger, and again, points in the direction of the north on the compass. Okay. Magnetic field strength, ta-da! Still have really no good way to measure this. I mean, I guess we can be quantitative, and we can say that a field is stronger here as opposed to here, because if I jiggle the compass needle, it vibrates at a different frequency, or like rapidly as opposed to slowly. And I guess we could measure that frequency, but I don't know how that correlates. Like, what is field strength? Don't know. If we did this trick with multiple compasses in multiple spots, we'd end up with this picture. It does sort of seem like we could track the sort of, imagine that these compasses are little infinitesimal steps around a path in space. So we just put one compass next to each other, and make a chain of compasses. Their needles would, it appears, point in kind of a continuous direction. For example, we've got kind of a, if we talk about this one, we've got kind of a this wayness, because this one here points out away, and this one points up at an angle. So we've got kind of a that way sort of thing. And then this one points that way, but this one points, so we're going to kind of come back because this one's horizontal. So it kind of comes back this way, maybe like that or so. And then the farther out, we've got this kind of thing, maybe this kind of thing, maybe that, maybe that. So we could sort of connect these compass needles together and end up with a picture not unlike that. The field line represents the magnetic field orientation tangent to the field line. So if we talked about this point here in this picture, the magnetic field is pointing this way, tangent to that field line. If we talked about, let's say, this point along this, it's tangent to that field line from north, out from north, in towards south. And the only reason that's true, and that is not the other way around, is again that we're defining this based on the behavior of the north needle of a compass. The north pole of this magnet pushes away the north pole of the compass. So the north pushes away here and is attracted to the south pole on the other side. Field lines do not intersect because there can't be more than one direction of the magnetic. A compass can't point in more than one direction at a particular spot. If field lines intersected, which way would the compass needle point? Would it point tangent to that line, or tangent to this line. And since we don't have any, like there's no preference, we can't have that situation. Field lines do not intersect. Here's a real picture of field lines. If we take metal filings, shavings, little tiny pieces of metal, and introduce them to a magnetic environment, they will form what looks a lot like this picture. Okay, so far so good. Again, this is all phenomenological. This is all just based on observation. Although we can at this point say something about the, if my compass points towards what I've called geographic north. Now, the north arrow of my compass is repelled from the north end of a magnet and attracted to the south end, which means if my compass points north that way, if my compass needle, the north end of my compass points that way, then that has to be a south magnetic pole because north is attracted to south. So what we call the North Pole is actually the South Pole. Well, it's the magnetic South Pole. It's so funny to me, and it just feels so like made up on the spot. We call that direction north, and our compass needles point north. So we say that that's the north side of the compass needle, which is great, except that now that's got to be south. Which I suppose is the only way we could do that. Because if we said one side of my compass needle points that way, I called that north. So then the compass I'm looking at, the side that's pointing that way had better be the South Pole. So that way is south. And that's just confusing as hell. So we had to stay, all right, the compass points north because that's north, which means that's a south magnetic pole. It's not quite spot on. The rotational axis of the Earth does not quite align with the pole, the sort of dipole line between the magnetic north and south pole of the Earth, which we can call declination. Nor is the magnetic field at the surface horizontal. There's some upward or downward tilt to it depending where you are on the surface of the Earth, and we call that the inclination. So we've got the declination, which has to do with the fact that we're off the rotational axis a little bit. It's not quite north, it's something like north. And the inclination, because it's not quite a horizontal, there's actually some pitch to it. All right. We have determined experimentally that there is a smallest unit of charge that we can store on a thing. If you scuff your feet on the carpet, you acquire electrons. If you scuff your foot just the right amount, you can acquire 1 electron, but you cannot acquire half an electron. That's not a thing that happens, which means you're acquiring charge in the unit of 1 electron's worth of charge. And you can acquire a positive or a negative charge without also acquiring a matching positive charge. You're acquiring electrons, negative charges in isolation. So fine, I've got a bar magnet with a north side and a south side. So I would like just the north. So I cut it in half. But I don't get just the north. I get north and south twice. And you can continue doing this half again, half again, half again, to the atomic level, half again, and it will still be north and south. Proving a thing does not exist is tricky. I can't prove to you that pink elephants don't exist, because I would have to go round up everything everywhere and show you that none of them are pink elephants. But that would take an infinitely long amount of time, and we'd probably get bored. Like establishing that a thing is not found anywhere. How would you do that? How do you go to everywhere and look and see that it is not there? And how do I know it isn't moving in the meantime? Like if I were looking for one particular fish in the ocean and I looked here and it wasn't there, and then I looked here, but in the meantime it had swum from there to here, how do I know it isn't there somewhere? We have never, ever, ever observed anywhere we have looked for one, and we have tried to find a magnetic monopole just a north or just a south hanging out on its own. It is not a thing. And as far as I'm concerned, it is not a thing. It is an impossibility. There is no evidence in theory or in experiment for the presence of magnetic monopoles. Now, that doesn't mean that there aren't any, because I can't prove that, but I can argue very, very, very strongly on the basis of centuries of well-founded scientific inductive reasoning that they don't exist, because we have never, ever, ever, ever seen them to exist. Which is good, I suppose. It means that magnetic fields are always going to look like this. That they never intersect, and that they always, let's think about this. The magnetic field lines of a single magnet form loops. They close back at the magnet. Actually, this picture shows that. This field line starts from north, points out from north, comes back around to south, and then inside the material of the magnet continues from south to north inside the magnet. Electric field lines, electron. Electric field points radially inward from everywhere. Those electric field lines do not terminate. They point radially inward everywhere. If there's no such thing as a magnetic monopole, there's no way to have non-terminating field geometries like there was for electric charge. They have to loop, they have to close and terminate back on a pole. Even the field of two magnets, each field line drawn from the North Pole terminates at the South Pole of the other. So this is some sort of weird combination field, but none of these fields extend infinitely in any direction. They terminate at magnetic poles. Okay, all right. I still feel a little bit unhappy with the way we left the strength. This feels really like loose, definitionally. All right. I think that I think that's a thing. I think that if you were feeling like, well, that's pretty milk, pretty weak sauce. I think you're right. I think it is. It is very, very, very non-quantitative. So we look for a way to be more quantitative.
In this demonstration, I have a tube connected to this power supply. When I turn on the power supply, we get a nice beam of electrons flowing from here to here. Now I also have a magnet, South Pole, North Pole, and what I'm going to do is I'm going to bring the South Pole up towards this end of the tube. Now the question is, which way will the beam deflect? Will the beam deflect up? Will the beam deflect down? Will it deflect towards me? Will it deflect away from me? Or will it not deflect in any way?
What? Why would it deflect at all? Who said anything about it deflecting? Why this? I just spent like an hour. No, it wasn't an hour. It was like a half an hour. I just spent some time dissociating electric stuff from magnesia stuff. Why would a beam of electrons have any care at all about a nearby magnet?
So bringing the South Pole.
What? What? What just happened?
In this way cause the beam to deflect up. How can we check to see if this is correct? We need to use the right-hand rule.
Okay, well,
So
right-hand rule, what are you talking about? All right, wait a minute. Here is a modified version of the figure we just looked, of the sort of apparatus we just looked at. We've got a cathode, a source of negative ions, or negative charges. In this configuration, what we're actually doing is heating the cathode to the point where the atomic excitations are violent enough that the atoms literally shake off their own electrons. Once we shake them off, if we have a potential difference set up, we can accelerate them. Most of these electrons hit the disk, but some of them pass through. And we can detect them. I mean, I can't see electrons, but I could detect their presence with a photosensitive, a phosphor screen, so that when the electron smacks into it, it makes a spot of light. It's essentially what the guy in the demonstration was just doing. Here's another picture. Suppose we set things up so that there is a magnetic field up the page in the Y direction. Our cathode ray, our negative charges, are moving to the right. I expect to see the spot of light that allows me to detect the beam of electrons. I expect to see it at the x-axis, but it is not there. It is into the page in the negative z direction, shifted not in the direction of the magnetic field, not in the direction of the velocity, but in a direction perpendicular to both of them. I did not expect that. Well, now I need to test it. In all cases, we've got a right-handed coordinate system. I've rotated the system. X points to the right along the page, Z points up the page, and Y points into the page, away from the viewer. If the magnetic field is oriented in the negative Z direction, down the page, the electron beam is deflected in the positive X direction. If we switch the direction, the deflection is in the other direction, the negative X direction. A rightward field deflects things up in the Z direction. A leftward field deflects things down. A magnetic field in the same direction as the velocity of the electrons does nothing, and a magnetic field opposite the direction of the velocity of the electrons also does nothing. Does not deflect the beam at all. It just strikes the spot where we would expect it to. Okay, something must be deflecting, pushing, right? Pushing on these negative charges to cause them They were going in the y direction as labeled in this picture. But then the direction of their motion changes, which means there must have been some acceleration, which means there must have been some force. It perhaps goes without saying, if I turn off the magnetic field entirely, then I don't see any deflection. I see this scenario again. So if the magnetic field is not present, or if it is along the direction of travel, either direction, we don't see any effect. But if we orient it some other way, then we have some effect. So that must mean that this deflection is as a result of the magnetic field. I have no other choice, no other recourse than to say that the deflection in these cases was caused by the magnetic field. But that's great, because now we have a really precise way to measure field strength. We could tie it to the deflection of an electron beam. We can say that a beam of electrons going so and so fast. So we're talking about particular charges, QE, going so and so fast, is deflected so and so far, such that the speed is changed by so and so much, the velocity is changed by so and so much. I'll just label it a delta for now. So we could talk about like an angular deflection. We could talk about the extent to which the velocity has changed. We could talk about the acceleration, and then we could talk about the force, and we could interrelate the force, the charge, the velocity, and the magnetic field somehow, and use that as a way to define magnetic field strength, that this is a magnetic field that exerts a force F on charges Q that are moving with speed V. Hopefully. This force, this deflection, is reliably in a direction perpendicular to both the direction the electrons are originally going and the direction of the magnetic field. The magnetic field is along Z, the initial velocity is along Y, and the deflection is along X, mutually perpendicular. Same story here, it's just the other direction. Here, the speed is along Y, the field is along X, but the deflection is up the page in the Z direction. So we're always talking about a deflection, a force that is at right angles to both the velocity and the field. Okay. The force is a vector, and it's a vector that is perpendicular to both feel like I've seen this kind of thing before. Right-hand rule. We're talking about two vectors and a vector that is perpendicular to both of them. That feels like a cross product to me. And as soon as we talk about a cross product, we're talking about a right-hand rule. If we try this trick with an anode ray gun, such that we're sending positive ions into the region where there is magnetic field, we can use the right-hand rule to account for the mutual directions if we express it as velocity cross field equals force. Velocity, try like looking at the picture, try it with your hand. Velocity cross field, my thumb points up the page like it looks. If I make it go the other way, velocity cross into, ow, I break my knuckles. It's got to be velocity cross around into field, my thumb points down. Try it yourself, convince yourself that that's true. I'll give you a minute. But then I got to go back because these results, I just want to check them. So we're saying V cross B equals F, or at least is proportional to F. V cross B. Now V is in the Y direction, away from the viewer. The field points down, so my thumb points in the, oh shit, wait a minute. I just tried it and my thumb points that way. Maybe that's okay. These are electrons. V cross B could still point this way. But then if I multiply by the charge Q, which for an electron is negative, then whatever the vector result of the cross product is, I'm going to end up making it negative, which means we're talking about a force that way, which is exactly the kind of deflection we're talking about. Awesome. And that explains the lurking Q here in the definition. We didn't need it for the positive charge, V cross B, but we need it for the electron. It's V cross B, and we get the opposite result. So we know that there needs to be some accounting for the charge that is moving with velocity V in field B. Equal velocities, opposite directions. The negative sign, the polarity of the charge flips the direction. As tempting as it is, do not use the left hand to do that. We are working in a right-handed coordinate system. Always tie your left hand behind your back. Always the right-hand rule. One last thing, we want to make sure that if the field is parallel or anti-parallel to the velocity of these particles, that no deflection occurs. And we can do that if we keep the same definition. as a consequence of this definition. We have to be very careful. Well, we still do, but we defined electric field as the force that is felt per unit charge Q. The electric field lines and the force felt by charges were either parallel or anti-parallel. If the charge is negative, then the force is one way, but the field is the other way. But we never had any sort of perpendicularity going on. All we could do is change from one direction to the opposite direction to talk about field and force. There was never any second or third dimension going on. It was just one vector or the opposite. This is a fundamentally different story, and that means it's in the picture, but field lines and the force that is created by a magnetic field are not the same. Oops, I'm sorry. There we go. Field lines are not lines of force, not like electric field lines represented lines of force. This is a more complicated situation. The other slide that I just skipped past is just reminding us how the cross product works. A force of magnitude Q, V, B, sine of the angle between V and B. The force is still directed, mutually perpendicular. If it's a positive charge, according to the right-hand rule, if it's a positive charge, and then you reverse that if it's a negative charge. So the direction is handled by the right-hand rule. The magnitude is handled by the cross product. And I guess the magnitude would be handled by the cross. Yeah, you know what I'm saying. Now, if the cross product is our definition, this one, the force on a moving charge Q is always, by definition, perpendicular to its velocity, because that's how the cross product works. It's also has to be perpendicular to the field, so there's an orientational thing that we can do, but it will be perpendicular to the velocity. Just idly thinking about situations that I'm familiar with for which the force is always perpendicular to the velocity. It's funny, this time I think he's barking at me, because that's an unfamiliar sound. It makes me think about circular motion. A uniform field, a uniform magnetic field, in this case directed into the page. If at some instant the charge is here and its velocity is this way, V crossed into the page, my thumb points radially inward. Which is true no matter where we put it. Field points that way. Field points that, well, I guess as you're looking at it, this is going to be weird to do with my right hand. But I guess if I use my left hand, it'll look to you like it's my right hand. That feels complicated. Just, and also I'm going to get confused. On the page at the bottom there at point O, the velocity points to the right. If we then curl our fingers into the direction of the field, which is down, our thumb points up the page, which is, again, radially inward. This force that we're talking about is going to be radially inward and constant, which means we're talking about circular motion. This is centripetal force. It's centripetal force for a circle of some radius. We haven't said anything about the radius. Remember that centripetal force has a magnitude equal to mv squared over r. We are talking about a speed v, and apparently this charge has a particular mass m, but we haven't, what we're saying is that the magnetic force is going to be doing the centripetal job for this situation. If we can't change the speed, we can't change the kinetic energy. And if we can't change the kinetic energy, we can't do any work. And that's cool. What if we had some velocity component along the direction of the magnetic field? What if it wasn't entirely in a plane and the magnetic field was perpendicular to the plane? Well, okay, that parallel component, I can't affect that. That's the kind of thing where I don't get any deflection. That's this kind. Any velocity component parallel or anti-parallel to the field is going to stay put. So we're going to keep our velocity parallel to the field and move in a circular path of some radius in the plane perpendicular to the field. we'll get a helical path. The aurora from top down is caused by the motion of charged particles in Earth's magnetic field. Another example, another sort of application of this kind of motion is a bubble chamber used to explore particle physics. The collision of subatomic particles produces other subatomic particles whose identity we can identify from their trajectories in the bubble chamber. The collision of gamma radiation collided, that collision with an electron. The electron is kicked way out this way. And the collision produces other subatomic particles. Another electron. This one, how do we know it's an electron? Because it curves down. It's got to be negatively charged. We know it's negatively charged because of the way it's curling, and we know that its speed is less. We know that it's slow moving because it's describing a tighter circle. This other thing, because it's curling the other way, has to be positively charged. And it appears to have the same kind of behavior as the electron, which must mean it has the same mass because we're doing the same centripetal thing for each one. So it's a particle of positive charge, but the same mass as the electron, so we know that it is a positron. One of these exotic subatomic particles that we can normally only produce and track in these sort of high energy situations. If we rely on the fact that particles traveling with some velocity will be deflected by a magnetic field and by an electric field, we can sort of cross-match electric and magnetic fields to produce no deflection at all. Let's see what that looks like. So we've got an anode ray here. We've got a source of positively charged particles. So we've got a positive charged particle here. It's moving down the page in a magnetic field into the page. So down the page, magnetic field into the page. The force it feels is to the right. But this is a positively charged particle, and it will be accelerated. Well, it'll be acted on at any rate by the electric field set up between the positive and the negative plates here. That electric field of magnitude E will push to the left towards the negative plate with magnitude QE. If these particles have the right velocity, then the force QE from the electric field to the left will be equally as strong as the force QVB from the magnetic field, which was directed to the right. Which speed is that? Well, it's this one. So we call it a velocity selector because it's going to allow only particles traveling with that speed or something very close to it to continue propagating out the other side. Any other particle, if it's going too slow, this side won't be large enough and it'll be attracted to the negative plate. If it's going too fast, this side will be too large and it will be attracted to the positive plate, pushed that way by the magnetic field. For a negative charge, the forces are reversed, but that doesn't change the eventual conclusion. We've got the charge on this side, the charge on this side, we're still going to cancel it. So whether we're canceling a positive number or canceling a negative number, I mean, it's the same final conclusion. All right. Suppose we used that property, the fact that crosswise magnetic and electric fields can function as a velocity selector, to understand that this is a beam of electrons. We can use the twin ideas. We've got a cathode ray, which is emitting electrons, and those electrons are attracted to that plate, which is positive, maintained positive. So we're going to accelerate electrons through these anodes, towards these anodes at any rate. An electron accelerated through a potential difference has a kinetic energy, has a speed in this direction, has a known speed. Okay, so if I know what speed it is, and if I know the potential difference between the two plates, and I know the magnetic field strength that I'm setting up, I can say something about the properties of that charged particle. I can compare its charge magnitude to its mass. An electron accelerated through a potential difference has a kinetic energy. mv squared. Well, 1/2 mv squared. And that speed is related to the potential difference that we accelerated it through, q delta v. Is the work done moving a charge q through a potential difference. Hold on. the work done moving a charge is Q delta V, and that'll be the same as the kinetic energy that it's going to have after being accelerated from rest. So the speed it's going to have is, maybe the square speed it's going to have is 2Q delta V over M. Okay. But if we subject it to a magnetic field, it's going to be subject to a perpendicular force perpendicular to its velocity of magnitude QVB, and that's going to mean a circle of a particular radius because it's going to function like the centripetal force. I wrote that earlier. I just wanted to kind of put it all in one spot. It's going to function like the centripetal force for motion at this tangential speed in some radius. So if I can measure somehow the radius of the motion that the thing makes, can I say something about the properties of this moving object? So we've got QB equals MV over R. And if we take the square root of this, then we can talk about V. So we've got M over R square root 2Q potential difference over the mass. Okay, so I want to measure the radius and have that tell me something about Q over M. M in the numerator divided by radical M in the denominator gets us a radical M left. If we divide by Q on both sides, we've got the same situation upside down. Q on the bottom, radical Q on top is going to leave us with a radical Q on the bottom. So we got to cancel those. Okay, so now Q over M, if we multiply back to the other side, equals 1 over RB square root 2 delta V. And we could square both sides. So if you tell me what the field is, and you tell me the potential difference that was used to accelerate those electrons in the first place, and we can measure the radius of the circle that they make, we can find the ratio between the charge to the mass. There's a little bit more experimental, sort of observational information that I need to share with you. A compass held nearby a wire points towards geographic north like it's supposed to. A compass near a wire carrying current does not point north. Which means that electric currents can apparently affect the behavior of magnetic objects. I don't have too much to say about that yet. Apparently, the current traveling in this wire changes the magnetic field in the region experienced by the compass, which makes me think that it causes its own magnetic field. The magnetic field of the Earth exists and the compass points north, and then we turn on the current, and then that somehow manifests its own magnetic field, which superposes with the magnetic field of the Earth, and we end up with this result. And I am not equipped yet to talk about how or in what way a current in a wire manifests a magnetic field. I almost deleted this slide entirely, but I thought it was important so that I could leave this the way that it was. A moving charge creates a magnetic field? Well, yeah, okay. I mean, I guess that makes sense. If a current in a wire creates somehow a magnetic influence that the magnet or that the compass can detect, then but current is just moving charges. So yeah, if a current can do it, then I suppose a moving charge could do it too. I guess that's not so crazy a claim based on this flimsy evidence. But the rest of this slide is more in line with what we've seen so far. Magnetic field exerts a force on any other moving charge, and now I'm starting to think that current would also feel a force as a result of being in a magnetic field because a current is just moving charges. A magnetic field is a vector field. Let's use the symbol B. And we know now, because the force experienced by a moving charge Q that has a velocity V is determined by the equation that we wrote. We can identify the field strength according to what force. Ooh, hey, that means we know what units it should have. Hold on, let me write this down. F equals QVB. So this is newtons. Let me use braces. Newtons, coulombs, meters per second. And I'm interested in what units does magnetic field need to have? Well, it needs to have units so that when we multiply by coulombs, meters per second, we end up with newtons. So it's got to be newtons seconds per meter coulombs. Apparently. Newton seconds, that's impulse, which didn't really have, I mean, it's kilogram meter per second. And I guess we can like cancel the meters then. So it's kilogram per second per coulomb. Oh, that's weird. Is that real? Did I do that right? That's kilograms meters per second squared dot seconds over meters dot Coulomb, seconds, meters, kilogram. Oh, whew. I thought for a second I was going to end up with some sort of flavor of like coulombs per second and kilograms, which felt very strange. But this remaining seconds is in the denominator, so it's kilograms per seconds coulombs, which doesn't make any less sense, I suppose, but it doesn't make any more sense either. Okay. What would you like to call this? Let's call it Tesla. Newton meter per amp. Ooh. Newton meter, that's joules. That's interesting. Wait. Oh yeah. Yeah, we did have a coulomb per second lurking in there. It's seconds per coulomb, so it's upside down. So the amps goes in the denominator. Yeah, okay. Now, wait a minute. I don't think that's correct. Newton, seconds, coulomb, meters. Yeah, that's amps, but this M should not be here. Yeah. One Tesla is defined as 1 Newton per amp meter. That, I think, is a typo. I got ahead of myself because this slide also shows us the unit for magnetic flux, which we call the Weber, if we would like to be Germanic about it, or Weber. WB for Weber, or Weber. Tesla dot meter square. So this is magnetic field Tesla dot area. Okay, so apparently we're talking about magnetic flux, like we talked about electric flux back when we were talking about Gauss's law. I guess while we're here at this slide, the Gauss, speaking of Gauss's law, is another unit of magnetic field, and it's just orders of magnitude smaller than Tesla. The reason that Gauss is still used is that the field of the Earth, the magnetic field of the Earth, has a strength of about 1 Gauss, give or take, depending where you are and different things. I mean, it's close. Which means Tesla is just way too big. If we're talking about Earth-sized magnetic fields, we're always going to be talking about, tenths of millitesla, which is just annoying. So if we're talking about Earth-sized fields, it's common still to see Gauss. but it's just orders of magnitude. Okay, so what's the deal with flux? Exactly the same as it was. We can divide any surface into elements of area dA. And you've got your little area element here represented by a single vector perpendicular to that area pointing outward from the surface. If the magnetic field in a particular region points this way, then the flux we're interested in the component of it that is perpendicular to the surface or parallel to the area vector. Just like we did for electric field, finding the component parallel to another vector, that's the job of the dot product. And if we add up all these little differential area squares, we end up with an integral, just like we had for electric field. We're going to use the same symbol, phi, but we'll use the subscript b. And that's why back in when we were talking about Gauss's law, we always wrote phi sub e, even though there was no other kind at the time of flux. We knew that we were going to be doing it for magnetic fields as well. So we started the habit. Electric flux and magnetic flux are defined exactly the same way. If we can talk about flux, then we can talk about a version of Gauss's law. If we add up all the net total flux through a closed surface, we used to say that it was equal or proportional to the charge enclosed by that surface. There's no way to have net magnetic pole anywhere. If you have a north, you necessarily have a south. So there's no net magnetic pole. So we end up doing the same math, but we cannot have net Q enclosed. It's going to be zero. Pick any closed surface. Now, this is a planar figure. So instead of a surface, I'm going to draw a loop, any closed loop. I'm going to draw it in a different color. No, wait, did I select? No, hold on. Imagine the Gaussian kind of sphere that goes with this in 3 dimensions. But every time a field line goes through that surface on the way out, keep watching, it comes back in. Every time a field line goes out, keep watching, it comes back in. Every time field line goes out, it comes back in. The net flux through the surface, just like through this loop, will be zero because every single field line enters and leaves. No field lines terminate and no field lines proceed to infinity. We never get a chance to have a net pile of field lines passing out or in to a surface if we're talking about magnetic field, because they all loop. All the field lines are closed in the looping sense. So yet another explanation for the fact that the net flux through a closed surface, the net magnetic flux through a closed surface, has to be zero. That's what I didn't want to do before, but here we are because it caused so many problems before. The total magnetic flux through any closed surface is zero, just all the time, for magnetic flux. It's Gauss's law. Magnetic flux through a closed surface used to be electric flux through a closed surface, but now we're talking about magnetic flux, and the answer is always zero because A, there are no magnetic monopoles, B, magnetic field lines do not terminate, they are loops. Here's some information about field strengths of various things. A long, straight current carrying wire creates its own magnetic field, which we have seen, right? I showed you a little bit of, or like one slide about that. So we could use compasses to determine the direction, and the direction is that it loops around the current carrying wire. Now, if a current carrying wire produces its own magnetic field, then that magnetic field can interact with another one, and there might be some forces involved, just like those two refrigerator magnets exerted forces on each other. Each creates their own magnetic field, and they exert mutual forces on each other. So a magnetic field that exists can interact with a current carrying wire. And we've sort of said this already too. If a magnetic field that exists acts on moving charges, which we've seen some evidence of that, a current is just a bunch of moving charges.